Good morning, good afternoon, good evening, whatever time you're watching this educational video. Tonight we will be doing work problems, but this time we will incorporate work kinetic energy theorem. And as we all know, the North Star of it, it could be applicable or it can be applicable in just forces that are conservative forces, meaning the forces are conserved. So we can say work is equal to change in ME. We will be using this equation later on. Okay, and always remember work is force times cosine theta. But before we will do the math, don't forget to support this channel. This is the problem. A space probe was launched from 275 meter per second. 275 meter per second, it's our initial velocity here. Then its mass of the space probe is 474. Of course, this is the mass. No other forces act on it except the 5-6 millinewton from the unit newton. It's going to be the force. Then on its engine, the displacement recorded is this figure here, 2.42 times 10 raised to 9. This is our displacement. And figure out the final velocity. This is our target using the work kinetic energy theorem of the probe, assuming that the mass never changes. So we have our conversion here. 1 millinewton is equal to 0.001. Let's do it. Let's have the given first. The given are our initial velocity, 275 meter per second. We have the mass of the probe, that's 479 kilogram. We have the force, 56 millinewton. We will convert it now to Newton. In our conversion factor to cancel mn, we can put it in the denominator and we have Newton in the numerator. So 1 millinewton is 0.001 Newton. So just multiply 56 times 001. 56 times 0.001, the answer is 0.056 Newton. This is our converted unit. And what else? We have the displacement. It's 2.42 times 10 raised to 9 meters. As you notice, the displacement is positive, so it's going to be right or up. And the force is also positive, so they are in the same direction. So the angle there is 0. As you all know, to get work is equal to force times displacement cosine theta, and cosine 0 will give you 1. So if we will put or replace cosine theta with 1 here, the answer is still FD. So no need to put it at this very moment. Let's continue. We will be using the work is equal to change in ME, and we can break it down to, since there's a change in ME, so we have ME final minus ME initial. And what is mechanical energy, or ME? ME is just the sum of KE plus PE. And what particular energy carries the unknown that we need to find, which is the final velocity, since it's moving. So our potential energy will be 0 in this case because our system is a moving probe. So we can have ME is just the KE. Okay. And remember, the formula of KE is 0.5 mass velocity squared. For PE, it's just mass, gravity, and then the height. So since PE is 0, so we can further simplify our formula to work is equal to, instead of KE, we can have KE final minus KE initial. And to isolate final, since we need to find the final velocity, and the final velocity is hidden in KEF, so we can move this term to the other side. So work positive, the positive KE plus the positive KEI, since we move it to the other side. So negative becomes positive in KEF. We will be using this formula. We will write KEF here. KEF is equal to work plus KEI from our formula. And we will put the formulas of each variable here. So K kinetic energy is 0.5 mass velocity squared is equal to work force displacement plus kinetic energy 0.5 velocity or velocity squared times the mass of the object. And take note, final kinetic energy, so it carries the final velocity. Initial kinetic energy, it carries the initial velocity. Let's continue. Let's plug in all the given. 0.5, the mass is 47479. Let's make it sure. 474. It's not 479. It's gonna be 474. So we will replace it here with 4 kilogram and then multiplied by the VF squared, our unknown. The force in the problem, as we converted, it's 0.56 Newton multiplied by the distance of 2.42 times 10 raised to 9 meter. Plus, since I don't have any space here, I will put it below. Plus this term, 0.5, then the mass 474, then the velocity times the velocity of 275 meter per second squared, the initial velocity. 0.5 times 474, the answer is 237 kilogram, and the unknown VF squared equals, let's multiply first this term, 0.056 times 2.42 times 10 raised to 9. The answer is 1, let's write it carefully, 135,520,000, and the unit Newton and meter, so you'll have Newton meter. Next is the terms below, plus 0.5, 0.5 times 474 times 275 squared. Don't forget to square it out. It will give you 179,23125. And the unit, kilogram meter per second squared, kilogram meter per second. And we square it up, so meter squared, second squared. And remember, kilogram meter squared, second squared, it's just the Newton meter. So we can change this unit for uniformity, Newton meter. Don't forget to square 275 times 275, meter times meter, seconds times seconds, and then you will multiply it by 474 and 0.5. It will give you this answer here, 179,23125. So let's continue. On the left side, 237 kilogram VF final squared is equal to, let's get the sum of it, 179,23125 plus 135,520,000, and the sum is 1,153,443,125 Newton meter. And to isolate VF, we will divide both sides by 237 kilogram. Cancel. So we'll have VF squared equals the quotient of it. Let's divide it by 237. So the answer is 647,439.346, and the unit Newton meter could be written as kilogram meter squared second squared over kilogram. Cancel kilogram. The remaining unit is meter squared second squared. We will get the square root of each side because we need to isolate VF. So let's get the square root. Cancel the radical and the squared. VF is equal to the square root of our answer. It's gonna be it's gonna be 804 times 63, 61575, or we can cancel squared here and the radical, so the remaining unit is meter per second squared, or we can simplify it or clean it up to 804.64 meter per second. This is the final velocity of our space probe using the kinetic or the work kinetic energy theorem. I hope you learned something, and yeah, see you until next time. Bye for now.